Okay, so when implicit conversion occur, the compiler automatically converts operands in the following circumstances. In most expression, values of integral types smaller than int are first promoted to an appropriate larger integral type. Okay. In conditions, non-bool expressions are converted to bool. In initialization, the initializer is converted to the type of the variable. In assignment, the right hand operand is converted to the left type of the left hand. In arithmetic and relational expression with operands of mixed type, the types are converted to a common type. Right. As we see in chapter 6, conversions also happen during function calls. Okay. Then we have the arithmetic conversions. The arithmetic conversions which we introduced here convert one arithmetic type to another. The rules define a hierarchy of type conversion in which operands to an operator are converted to the widest type. Right. For example, if an operand is a long double, then the other operand is converted to a type long double regardless of what type is. More generally, in expression that mix floating point and integral values, the integral values is converted to an appropriate floating point type. Integral promotions. The integral promotions convert the small integral types to a larger integral type. The types bool, char, signed, char. Acha, oh, bool, char, signed char, unsigned char, short, and unsigned short are promoted to int if all possible values of that type fit in an int. Otherwise, the value is promoted to an unsigned int. As we have seen many times, a bool is false. A bool that is false promotes to 0 and true to 1. The larger char types, are promoted to smallest type of int, unsigned int, long, unsigned long, long long, or unsigned long long, in which all possible values of the character type fit. Alright. We have operands of unsigned type. If the operands of an operator have differing type, those operands are ordinarily converted to a common type. If any operand is an unsigned type, the type to which the operands are converted depends on the relative sizes of the integral types of machine. Okay. As usual, integral promotions happen first. If the resulting types match, no further conversion. Okay, if the resulting types match, no further conversion is needed. If both possibly promoted operands have the same signedness, then the operands with the smaller type is converted to the larger type. When the signedness differs, the type of the unsigned operand is the same as or larger than that of the signed operand. The signed operand is converted to unsigned. Okay. For example, given an unsigned int and an int, the int is converted to an unsigned int. It is worth noting that if the int has a negative value, the result will be converted with the same results. Okay. The remaining case is when the signed operand has a larger type than the unsigned operand. In this case, the result is machine dependent. If all the values in the unsigned type fit in the larger type, then the unsigned operand is converted to the signed type. If the values don't fit, then the signed operand is converted to the unsigned type. Okay. So for example, if the operands are long and unsigned int, and int and long have the same size, long will be converted to unsigned int. If long type has more bits, then unsigned int will be converted to long. Right. Okay, understanding the arithmetic conversions. So we have a is promoted to int, then int converted to long double. Okay, ival converted to double, then we dval converted by truncation to int, and if dval is 0, then flag is false, otherwise true. Okay, cval is converted to int, and then it is converted to float. Sval and cval, sval short, are promoted to int. then this will be promoted to long, this will be unsigned long, and this will be okay unsigned short. Promotion depends on the sign of unsigned size of unsigned short and int, and unsigned integer and long depends on the size of unsigned int and long. Okay. Given the first addition on the character constant lowercase is type char, which is a numeric value, what the value what the value is depends on the machine's character set. On a machine has numeric value 97. When we add to now the char value is promoted to int and the int value is converted to long double. The converted value is then added to the literal. The other interesting cases are the last two expressions involving unsigned values. Okay. We have given the variable definitions in this section. Explain what conversion takes place in the following. This gets converted. Okay. So this gets converted to bool. Then int promoted to float, then float promoted to double. Okay. Okay, so we'll go first char is promoted to int, then the result is promoted to double, right? Double, and I will convert it to double. Okay, given the following definitions, identify the implicit type conversions, if any, taking place. See well. Okay, so we'll say is promoted to int. But both of these are values and it can fit. None here. I don't think so. Unsigned int, right? Okay. So we have depends on size of UI. If greater, right? Unsigned short and int, unsigned int and long. Okay. I think, yeah. Okay. Here I will be promoted to float, then result is converted to double. Okay, so you can say ival promoted to float, then UI promoted to float. Okay, So if val promoted, okay, so I val promoted to float, result is promoted to double, then the whole thing is truncated to char. I just have to check if any implicit conversion is going on here. Let's see, Gemini. Identify any implicit conversion happening here. In many programming, char is used in key table. Okay. Okay. Cval is of type char. Then will there be any implicit conversions? Conversion. Here's the breakdown of two implicit conversion. Integer promotion of the, yeah. Okay, so in all, okay, okay, so in arithmetic expression, arithmetic expression, all types are promoted to int first. Then truncated to fit. What is up with this? Okay. And we have other implicit conversions. In addition to the arithmetic conversions, there are several additional kinds of implicit conversions. These include array to pointer conversion. Okay, in most expression when we use an array, the array is automatically converted to a pointer to the first element in that array. Okay. This conversion is not performed when an array is used in the decal type or as the operand of the and of size of or type ID. Okay. The conversion the conversion is also omitted when we initialize a reference to an array. And a similar pointer conversion happens when we use function type in an expression. Pointer conversions. There are several other pointer conversions. A constant integral value of 0 and the literal null PTR can be converted to any pointer type. Note, a pointer to any non-const type can be converted to void, and a pointer to any type can be converted to a const void. Okay, we'll see that there is an additional pointer conversion that applies to types related by inheritance. Okay, we'll see. Saying that a constant integral value 0, the literal null pointer can be converted to any pointer type. Okay, a pointer to any non-const type can be converted to void, and pointer to any type can be converted to a const void. Okay, conversions to bool. There is an automatic conversion from arithmetic or pointer types to bool. If the pointer or arithmetic value is 0, the conversion yields false, and any other value yields true. Okay, conversion to const. We can convert a pointer to a non-const type to a pointer to corresponding const type. Okay, we can convert a pointer to a non-const type to a pointer to corresponding const type, and similarly for references. That is, if t is a type, we can convert a pointer of reference t into a pointer of or reference. Okay, we can convert to a pointer or a reference to t and a pointer or reference to const t respectively. Okay. Okay, so int I, then we have a const reference to I, and we have a const pointer to I, and we say then this is a simple reference j, and we also have a simple. Okay, so convert a non-const to a reference, convert a non-const to a reference to const int, const. Okay, convert address of a non-const to the address of a const. Conversion from const to non-const not allowed. The reverse conversion, removing a low-level const, does not exist. Okay. Then we have conversions defined by class types. Class types can define conversions that the compiler will automatically apply. The compiler will apply only one class type conversion at a time. We'll see an example of when multiple conversions might be required at a time. Our programs may have already used class type conversion. We use a class type conversion when we use a C style string when a library string is expected, and when we read from an stream in a condition. Okay. Then we have the condition reads cin and yields cin as its result. Conditions expect a value of type bool, but this condition tests a value of type istream. The IO library defines a conversion from istream to bool. That conversion is used automatically to convert cin to bool. The resulting bool value depends on the state of the stream. If the last bit succeeded, then the conversion yields true. If the last attempt failed, then the conversion to bool yields false. Okay, then we have explicit conversions. Sometimes we want to explicitly force an object to be converted to a different type. Okay, to do so, we need a way to explicitly convert. Use cast. We use a cast to request an explicit conversion. Although necessary at times, casts are inherently dangerous constructs. Okay. Then we have named casts. A named cast has the following form, where type is a type. where type is a target type of the conversion and expression is the value to be cast. If type is a reference, then the result is an L value. The cast name the cast name may be one of the following. Okay, static cast, dynamic cast, const cast, and reinterpret cast. We'll, we'll cover dynamic cast, which supports the runtime type identification, and here then the cast name determines the what kind of conversion is performed. Okay, static cast. Any well-defined type conversion other than those involving low-level const can be requested using a static cast. For example, we can force expression to use a floating point division by casting one of the operand to double. Okay, static cast double. A static cast is often useful when a larger arithmetic type is assigned to a smaller type. The cast informs both the reader of the program and the compiler that we are aware of and are not concerned about the potential loss of precision. Compilers often generate a warning for assignment of a larger arithmetic type to a smaller type. When we do an explicit cast, the warning message is turned off. A static cast is also useful to perform a conversion that the compiler will not generate automatically. For example, we can use static cast to retrieve a pointer value that was stored in void pointer. Oh. Okay. Address of any non-const object can be stored in a void. Okay, convert void back to original pointer. Okay. When we store a pointer in a void and then use a static cast, okay, when we store a pointer okay, and then use static cast to cast a pointer back to its original type, we are guaranteed that the pointer value is preserved. That is, the result of the cast will be equal to the original address value. However, we must be certain that the type to which we cast the pointer is the actual type of the pointer. If the pointer do not match, the result is undefined. Okay, const cast. A const cast changes only a low level const in its operand. Okay. Okay, constant changes only a low level const in its operand. Okay. Okay, but writing through P is undefined. Conventionally, we say that a cast that converts a const object to a non-const type casts away the const. Once we have cast away the const of an object, the compiler will no longer prevent us from writing to that object. If the object was originally not a const, using a cast to obtain write access is legal. However, using a const object in order to write to a const object is undefined. Only a const may be used to change the constness of an expression. Trying to change whether an expression is a const with any of the other forms of named cast is a compile time error. Similarly, we cannot use const cast to change the type of an expression. Okay. Static cast char p is error. Okay. Const cast string. Okay, we are here. We are converting. Okay. To string. Okay, const cast string cp error const cast only changes the constness, cannot change the type. Okay. A const cast is more useful in the context of overloaded function, which we'll describe here. Then we move on to reinterpret cast. A reinterpret cast generally performs a low-level reinterpretation of the bit pattern of its operands. Okay, so we have an int pointer and we are reinterpreting it to char pointer. We must never forget that the actual object addressed by PC is an int, not a character. And any use of PC that assumes it's an ordinary character pointer is likely to fail at runtime. For example, is likely to result in a bizarre runtime behavior. Okay. The use of PC to initialize str is a good example of why reinterpret cast is dangerous. The problem is that the types are changed, yet there are no warnings or errors from the compiler. When we initialize PC with the address of an int, there is no error. There is no error or warning from the compiler because we explicitly said the conversion was okay. Any subsequent use of PC will assume that the value it holds is a char start. The compiler has no way of knowing that it actually holds a pointer to an int. Thus, the initialization of str with PC is absolutely correct, albeit in this case meaningless or worse. Tracking down the cause of this sort of problem can prove extremely difficult, especially if the cast of IP to PC occurs in a file separate from the one in which PC is used to initialize a string. Okay. A reinterpret cast is inherently machine dependent. Safely using reinterpret cast requires completely understanding the types involved as well as the details of how the compiler implements the cast. Okay. Then we have old style casts. In early version of C++, an explicit cast took one of the following two forms: type, expression, or function style C language. Okay. Void casts. Okay. Casts interfere with normal type checking. As a result, we strongly recommend that programmers avoid casts. This advice is particularly applicable to reinterpret casts. Such casts are always hazardous. A const cast can be useful in the context of overloaded function, which we'll cover here. Other uses of const cast often indicate a design flaw. The other casts, static cast and dynamic cast, should be needed infrequently. Every time you write a cast, you should think hard about whether you can achieve the same result in a different way. If the cast is unavoidable, errors can be mitigated by limiting the scope. Errors can be mitigated by limiting the scope in which the cast value is used and by documenting all assumptions about the types involved. Then depending on the types involved, an old style cast has the same behavior as a const cast, static cast, or a reinterpret cast. When we use an old style cast, where a static cast or a const cast would be legal, the old style cast does the same conversion as a respected named cast. Okay. If neither cast is legal, then an old style cast performs an reinterpret cast. For example, has the same effect of using a reinterpret cast. Old style casts are less visible than the named cast because they are easily overlooked and it is more difficult to track down a rogue cast. Okay, assuming I is an int and d is a double, write the expression so that it does integral rather than floating point multiplication. Okay, so it want I equals to, let's say, static cast int, and then we go d. I think this should work. Let's try exercise 4.11.3. Section 4.11.3, and this is 4.36. Then 4.36.cpp. Okay, so I have int I equals, let's say 42, and double d equals 3 point, let's say 2.45. Okay, then I'll do static cast to int d. See if 42 times 2 is 84. Right. Okay, rewrite each of the following old style cast using a named cast. Okay, so PV is a void pointer, PS, okay, pointer. So I would say that PV equals, we're statically casting. Okay, this is not static cast, I think this is reinterpret cast that we are. And I also want to remove the constness. So if I want to remove the constness, I will use a const cast, but okay, I'm removing constness, void pointer PV. Okay. PV const cast. Okay, wait, I'm not doing this one first. Okay, so I equals PC char. Okay, so okay, int, right? So I am statically casting the value. So int I is static cast int and then value of PC. Okay, then we have PC and char PV. Okay, so I'm simply removing the const cast char, and then we'll go with PC. Okay, so I'm removing the PV void pointer reference, void reference. Okay, explain the following. This would convert the result of the integer division to double, which would which would where precision will be lost. Okay, so reference. Okay, not reference. I'm PV. I think this is okay, right? Void pointer named cast. This is okay. Okay, as okay, because the scan, right? It is just a. It can do that. It is okay. Okay. So now I have PV void pointer PS. I think I have to use a reinterpret cast. Because I'm changing the internal. Yeah. PV equals reinterpret cast to void pointer for PS. Cost string. Bruh. Are you okay? Thank you. Reinterpret cast. Okay. Let me try. Let me ask this. How to perform this using C++. Okay. Which cast, that is static cast, const cast or reinter for this expression. Okay, C style static cast. Okay, use const to remove const qualifier from PS. Okay, so it used a const to remove the const, and then, okay, correct. This is void shortened for two step that you must use a const to remove the const qualifier. Okay. Then we have const cast char star PC. First we will remove const, then reinterpret it. Pet slash, then use we interpret slash static static cast. Okay, then we have operator precedence table. Alright, okay, chapter summary. The smooth operator. Okay, C++ provided a set of operators and defines their meaning when applied to values and print type. Additionally, the language supports operator. Okay, operator overloading, which allows us to define the meaning of operators for class type. We'll see it here. To understand expressions involving more than one operator, it is necessary to understand precedence, associativity, and order of operand evaluation. Each operator has a precedence, level, and associativity. Precedence determines how operators are grouped in a compound expression. Associativity determines how operators at the same precedence level are grouped. Most operators do not specify the order in which operands are evaluated. The compiler is free to evaluate either the left or right hand operator first. Okay. Often the order of operand evaluation has no impact on the result of expression. However, if both operands refer to the same object and the operand changes the object, then the program has a serious bug, and that bug that will be hard to find. Okay. Finally, operands are often converted automatically from their initial type to another related type. For example, small integral values are promoted to a large integral value. Conversion exists for both built-in and class types. Okay. Then we move on to chapter number 5. Okay. Like most languages, C++ provides statements for conditional execution loops that repeatedly execute the same body and jump statements that interrupt the flow of control. The chapter looks in detail at the statements supported by C++. Okay, what do we have? Try, blocks, and exception handling. Ooh. We have jump statements, iterative. Okay. The statements are executed sequentially. Except for the simplest programs, sequential execution is inadequate. Therefore, C++ also defines a set of flow of control statements that allow more complicated execution paths. Okay. Simple statements. Most statements in C++ end with a semicolon. An expression such as ival plus 5 becomes an expression statement when it is followed by a semicolon. Okay. Expression statements cause the expression to be evaluated and its result discarded. Okay. The first statement is pretty useless. The addition is done, but the result is not used. More commonly, an expression statement contains an expression that has a side effect, such as assigning a new value to a variable or printing a result when it is evaluated. Null statements. The simplest statement is the empty statement, also known as a null statement. A null statement is a single semicolon. Okay. A null statement is useful where the language requires a statement, but the program's logic does not. Okay. So such usage is most common when a loop's work can be done within its condition. For example, we might want to read an input stream ignoring everything we read until we encounter a particular value. The condition reads a value from the standard input and implicitly tests cin to see whether the read was successful. Assuming the read succeeded, the second part of the condition tests whether the value we read is equal to the value in sort. Okay. If we found the value we want, the while loop is executed. Otherwise, the condition is evaluated again, which reads another value from cin. Null statement should be commented. That way, anyone reading the code can see that the statement was omitted intentionally. Beware of missing or extraneous semicolons. Because a null statement is a statement, it is legal anywhere in a statement is expected. For this reason, semicolons that might appear illegal are often nothing more than null statements. The following fragment contains two statements: the expression and the null statement. Okay. Second semicolon is superfluous. Null statement. Although an unnecessary null statement is often harmless, an extra semicolon following the condition in a while or if can drastically alter the program's intent. So for example, the code will loop indefinitely, right? Contrary to the indentation, the increment is not part of the loop. The loop body is the null statement formed by the semicolon that follows the condition. Extraneous null statements are always harmless, not always harmless. Okay. Compound statement blocks. A compound statement, usually referred to as a block, is possibly empty sequence of statements and declarations surrounded by a pair of curly braces. A block is a scope. Names introduced inside a block are accessible only in that block and in the block nested inside that block. Names are visible from where they are defined until the end of the immediately enclosing block. Compound statements are used when the language requires a single statement but the logic of a program needs more than one. For example, the body of a while or for loop must be a single statement. Yet, we often need to execute more than one statement in the body of the loop. We do so by enclosing the statement in curly braces, thus turning the sequence of statements into a block. As example here, okay. The logic of program needed two statements. The logic of a program needed two statements, but a while loop may contain only one statement. Enclosing these statements in a curly braces, we made them into a single compound statement. A block is not terminated by a semicolon. Okay. We can also define an empty block by writing. We can also define an empty block by writing a pair of curlies with no statement. An empty block is equivalent to a null statement. Okay. What is a null statement? When you might use a null statement like in for and while. Okay. Single semicolon null statement, maybe mostly used with loops. When work, when all the task can be done within the condition of the loop. What is a block? When you might use a block, is a block used used when we require more Diminishes the readability of the code. In some sense, it does diminish the readability. Okay, statement scope. We can define variable inside a control structure of if, switch, while, and for statements. Huh. Variables defined in the control structure are visible only within the statements and and are out of the scope after the statements ends. Okay. If we need to access the control variable, then the variable must be defined outside the statement. Okay. Now the value of an object defined in a control, the value of an object defined in a control structure is used by the structure. Therefore, such variables must be initialized. Okay. Okay. Explain the following example and correct any problems. Iterator. String iterator is created and initialized on iteration. Accessible out of loop. Okay, I would have to look into this. So we'll say I'll continue this tomorrow.